Hello everyone. Good afternoon guys. Good evening guys. Good evening. Good evening everyone. Okay, so audio and video is clear from my side. I hope it is clear from your side as well. Please tell me about audio and video. Please tell me about audio and video everyone. Tell me whether my audio and video is clear or not. Tell me everyone. Okay, I hope it is clear. So I hope your preparation is going well. So in the previous class we were discussing about Nyquist plot, and if you remember I told you how to do the mapping process. Okay, so the mapping was very lengthy, and to map the complete right half contour is a lengthy process. So I will tell you the trick also, how to use a direct trick, and by which you can map and you can see the stability of the closed loop system. But first let's look at the application of the Nyquist plot. So till this time, till this class, I have told you in the previous two classes, I just taught you about the mapping only. Okay, how to do the mapping process and how to check the encirclement. Okay, that two things I have told you. Now in today's class, we'll look at the application of the Nyquist, how we are going to use Nyquist plot in checking the closed loop system stability. Okay, so today's class is all about Nyquist plot and checking of the closed loop system stability. For that we will use the Nyquist, and how we are going to use that Nyquist, and how we are going to use the previous concept that we have studied just before. Okay, now so let's first cover the introduction part, and then I will start the session. Okay, so this is my introduction. My name is Asu Jangra guys, and you can start your preparation with me, and I teach almost every subject. So you can join BYJU'S exam prep and you can start your preparation with me. There is free scholarship test which will be on 23rd of July at 9 p.m. So you can register for that. The link is given in the description. So you can get the scholarship up to 90%. Let's say you are not good at, your financial condition is not good, then you can appear this test and you can join BYJU'S exam prep. Okay. There is free workshop which will be on 25th of July at 7:30 p.m. This will be taken by Dheeraj Sardana sir. So you can join this free workshop, and the title of the workshop is In-Depth Preparation Strategy for GATE 2024. So again, it's very useful. So you can join this free workshop. Link is given in the description. You can register for it. Now it's time for Guru Dakshina. So Guru Dakshina, you have to subscribe our channel. You have to press the like button, and you have to press the bell icon so that you get the notification whenever my sessions are live. Okay. So guys, let's start our session. So in the previous class, if you remember, I told you how to do the mapping. Now today's agenda is application. Okay, application of Nyquist. Today's agenda is application. Okay, how to apply this Nyquist concept in checking the closed loop system stability. Before going into that, I'm telling you 2 points that you need to remember. Let's say we have provided with some GSHs. Some GSHs is like this: K naught into S plus Z1 divided by S plus P1, S plus P2. Let's say this is my GSHs. Now the zeros of GSHs are minus Z1, and the poles, finite poles, are minus P1 and minus P2. So these are the finite poles, these are the finite zeros. These are the poles and zeros of open loop system, GSHs. Now I want to find the characteristic equation. The characteristic equation is 1 plus GSHs, because I want to find the closed loop system pole and zeros. So if you want to find the closed loop system, then the closed loop system transfer function will be GS divided by 1 plus GSHs. And to find the closed loop poles, to find the closed loop pole location, you have to write the characteristic equation. So the characteristic equation is this. This is my characteristic equation, and the roots of this equation will be the poles of the closed loop system. Now if I simplify this characteristic equation, if I simplify and if I put this value, so it will be 1 plus K naught into S plus Z1 divided by S plus P1 into S plus P2. Fine. So if I take the LCM, it will look like this: S plus P1 into S plus P2 in the denominator, and in the numerator you will have S plus P1 into S plus P2 plus K naught into S plus Z, S plus Z1, let's say. So this is my characteristic equation, guys. Let me simplify this. The denominator is S plus P1, S plus P2. In the numerator, we have quadratic equation. So again, there will be two roots of this equation. So I'm writing like this: S plus Z1 prime, S plus Z2 prime. And there is some K naught prime, constant value. Okay. So you can say that this is the characteristic equation. Yeah, you can put it equal to 0. This is the characteristic equation. And we know that the roots of the characteristic equations are the poles of the closed loop system. Now, can you find the roots of the characteristic equation? Yes, we can find the roots of the characteristic equation. Tell me the roots of characteristic equation. What are the roots of characteristic equation? Roots of characteristic equation, or you can say poles of closed loop system. Poles of closed loop system. Closed loop system. Tell me, guys. So the roots of the characteristic equation or poles of the closed loop system are minus Z1 prime, minus Z2 prime. If you put it equal to 0, then the value of S will be minus Z1 prime and minus Z2 prime. Now what you can conclude is, now what you can comment on these analysis on this screen, what you can conclude is there are 2 points, 2 important points that you need to remember. And those points are the poles of GSHS. Look, the poles of GSHS and the poles of 1 plus GSHS. This is the 1 plus GSHS function. Okay. 1 plus GSHS we have found. So this is 1 plus GSHS. So you can say that the poles of GSHS and the poles of 1 plus GSHS are same. You can see that the poles of 1 plus GSHS are minus P1 and minus P2, and the poles of GSHS are also minus P1 minus P2. Now there is one interesting point. That point is the zeros of 1 plus GSHS. The zeros of 1 plus GSHS are actually the poles of closed loop system. You can see that the zeros of this 1 plus GSHS are the poles of closed loop system. It means the zeros of 1 plus GSHS, the zeros of 1 plus GSHS will tell us about the closed loop system stability. The zeros of GSHS will tell us about the closed loop system stability. So we are interested in the zeros of 1 plus GSHS because the zeros of 1 plus GSHS are actually the poles of the roots of the characteristic equation, or simply you can say poles of the closed loop system. So we are more interested in the zeros of 1 plus GSHS. I hope it is clear. So you have to be very clear about it. So there are 2 points that you need to remember. Let me repeat this again. First point is the poles of GSHS and the poles of 1 plus GSHS. This is 1 plus GSHS, and the poles of 1 plus GSHS are same. Poles of GSHS and poles of 1 plus GSHS are same. This is the first point. The next point is the zeros of 1 plus GSHS are actually the poles of closed loop system. The zeros of 1 plus GSHS are actually the poles of the closed loop system. I hope it is clear. So these 2 points you need to remember because we are going to use it. Okay. Now how we are going to use these 2 points? Okay. Let me tell you how. Let's come to the next. Now, since you understand these 2 points, now we can use the Nyquist criteria to check the stability of the closed loop system. How to do that? Let's say I have selected S-plane contour and I have selected entire right half. So the S-plane contour is like this. Let's say this is the S-plane contour I have. I have selected this as the S-plane contour. Okay, so this is the S-plane contour, guys. This is the S-plane contour. So I have selected this as S-plane contour, and this S-plane contour contain the entire right half. Okay. Let me write it like this. This is j omega axis. Omega varies from 0 to infinity, and then the radius is r e to the power j theta. Okay. So this is again r tends to infinity. So it means it's an infinite radius circle. Okay, theta varies from plus pi by 2 to minus pi by 2, and then again j omega varies from infinity to minus infinity to 0. Okay, so this is the way you can define the entire right half. Okay, now let's say GSHS is provided to us. GSHS is provided to us. Okay, and GSHS is like this: K0 into S plus Z1 divided by S plus P1 into S plus P2. Let's say this is my GSHS. I'm taking a random function, okay, random values like this. Okay, this is my GSHS. Now if you map this S-plane contour into this function, let's say, if you map this S-plane contour into this function, let's say the final result, the GS, you are mapping into GSHS, okay? You are mapping into GSHS. Let's write it like this: S plus P3 also, and here S plus Z2 also. So it's a random function. What you are doing is you are mapping this S-plane contour into GSHS, and the resultant contour is let's take a random function. Let's say this is the resultant contour. You have mapped this S-plane into GSHS, and you get this as the GSHS plane contour. So this is the mapped plane in the or you can say that in GSHS plane you have mapped this S-plane. You have mapped this S-plane contour into GSHS plane, and this is the final contour. Now if you look at the encirclement of origin, then that encirclement will be equal to P minus Z, or you can say Z minus P. Now what is this P and what is this Z? If you are looking the encirclement of origin, what is this P and what is this Z? P is the poles of GSHS inside S-plane contour, inside S-plane contour, inside S-plane contour, and Z is the zeros of GSHS inside S-plane contour, inside S-plane contour. Okay, if you are mapping this S-plane into GSHS plane, and if you are looking at the encirclement of origin, then that encirclement will be P minus Z, and P is the number of poles of GSHS inside this contour, and Z is the number of zeros of GSHS inside this contour. Okay, this way you can calculate the number of encirclement, and you can get the information about poles and zeros inside this contour. Okay, now let's say what you are doing is, again I have the same GSHS, but this time I am not mapping into GSHS, I am mapping into 1 plus GSHS. Okay, this is 1 plus GSHS. I am mapping into 1 plus GSHS. Okay, it means what I am doing is I am taking this entire S-plane contour and I am mapping into 1 plus GSHS plane. Okay, I am mapping into 1 plus GSHS plane, and let's say the resultant contour is like this. This is the resultant contour. Wait a minute. The resultant contour is, if you are mapping this S-plane contour into this function, then the resultant contour is somewhat like this. Okay, wait a minute. It's similar to this only. The only thing is it is shifted. Oh, okay guys. So I'm mapping into this S-plane contour. I'm mapping into 1 plus GSHS. So I want to draw this. I don't know how to draw it. Okay. So what I'm doing is, first I have mapped this S-plane contour into GSHS plane, and then I have mapped this S-plane contour into 1 plus GSHS plane, and I'm looking at the encirclement of origin. Please be careful. I'm looking at the encirclement of origin. Here also I'm looking at the encirclement of origin. Here also I'm looking at the encirclement of origin. Now in this case, if you are looking at the encirclement of origin in GSHS plane, then the number of encirclement of origin will be P minus Z. P is the number of poles of GSS and Z is the number of zeros of GSS. Okay. Now, if you are mapping this entire S-plane contour into 1 plus GSS, and if you are looking the encirclement of origin, then that encirclement will be again either P minus Z or Z minus P. But now this P and this Z are different. What is this P and what is this Z? P is the poles of 1 plus GSS inside S-plane contour. Inside S-plane contour. Okay, and Z is the zeros of 1 plus GSS inside S-plane contour. Inside S-plane contour. Okay, so you have to be very careful. If you are mapping this S-plane contour into GSS, and if you are looking the encirclement of origin, then that encirclement will be P minus Z or Z minus P. Now the meaning of this P and this Z are the poles and the zeros of GSHS inside this contour. But if you are mapping this S-plane contour into 1 plus GSHS, and if you are looking the encirclement of origin, then that encirclement is again P minus Z or Z minus P. Now the P and Z are different here. P and Z are the poles and zeros of 1 plus GSS because you are mapping into 1 plus GSS, okay? So that's why you have to be very careful. In which function you are mapping, that is important, okay? In which function you are mapping, that is important. Here you are mapping into GSS, here you are mapping into 1 plus GSS. And you are looking at the encirclement of origin. Okay, you are looking at the encirclement of origin. So here the encirclement of origin N will be equal to P minus Z. And we are more interested in the zeros of 1 plus GSS. If you remember, we are more interested in the zeros of 1 plus GSS. So if somehow we can get the value of pole, somehow we can get the information about the pole of 1 plus GSS inside this S-plane contour. If somehow we can get the information of pole, how many poles of this 1 plus GSS inside this S-plane contour, then we can calculate the Z values, the zeros of 1 plus GSS inside this S-plane contour, and we can get the stability. Because the zeros of 1 plus GSS are actually the poles of the closed loop system. If any poles lie in the right half of the S-plane inside this contour, if any pole of the closed loop system lies in the right half of the S-plane, the system will become unstable. It means if any zeros of this 1 plus GSS lie inside this S-plane contour, the closed loop system will be unstable. So we are more interested in the zeros of 1 plus GSS. Now how to get the information about the poles of 1 plus GSS? We know that the poles of 1 plus GSS and the poles of GSS are same. So it means if you know the poles of this GSS, you can easily know the poles of 1 plus GSS. This information you can get from GSS. And the number of encirclement you can get from the mapping, okay? If you have mapped this S-plane contour into 1 plus GSS, you can get the information of number of encirclement, and you can get the information of pole, then you can get the information about zeros, okay? Z you can find. And zeros of 1 plus GSS are actually the poles of closed loop system. We can easily find like this. But this is a difficult process. Why it is difficult process? Because it's not easy to map this S-plane contour into 1 plus GSS. Why? Because first you have to find this 1 plus GSS. If GSS is provided, first you need to find this 1 plus GSS. You have to take LCM and you have to find 1 plus GSS. And then you have to map. Then you have to map into this function. It's a lengthy process. It's a lengthy process. To map this S-plane contour into 1 plus GSS and look at the encirclement of origin, it's a lengthy process. So what you can do is, there is a trick. What is the trick? There is a simplified version. What is the simplified version? The simplified version is, we want to map into 1 plus GSS. We want to map the S-plane contour into 1 plus GSS because 1 plus GSS is my characteristic. This is my characteristic equation. So you are mapping S-plane contour into 1 plus GSS and looking the encirclement of origin. That encirclement of origin is P minus Z, where P and Z are the poles and zeros of 1 plus GSS inside the S-plane contour. But now I don't want to map into 1 plus GSS. I want to map into GSS. So from here, if you calculate GSS, it will be minus 1. You take this 1 on this side in characteristic equation. So what you need to do is, you need to map the S-plane contour into GSS And you have to look at the encirclement of -1. If you are mapping entire S-plane contour into GSHS, and if you are looking the encirclement of -1, it is the same thing that you are mapping this S-plane contour into 1 plus GSHS and looking the encirclement of origin. It's the same thing. Okay? So you have to be very careful. Either you map this S-plane contour into 1 plus GSHS or look at the encirclement of origin, or what you can do is you map this S-plane contour into GSHS and look at the encirclement of -1. You are doing the same thing. You are doing the same thing. Okay? This process, and in this, if you are mapping this S-plane in GSHS and looking the -1 encirclement, this process, these two processes are the same. I hope it is clear. So there are two ways to look at the number of encirclement of origin, or maybe of -1, or to check the closed loop system stability. What you can do is you can take this S-plane contour, you can map into 1 plus GSS and look at the encirclement of origin. That encirclement will be P minus Z, where P and Z are the poles and zeros of closed loop system. P and Z are the poles and zeros of 1 plus GSS, which are lying inside this S-plane contour. Either you do like this, you map into 1 plus GSS, or what you can do is, there is one more way, guys. There is one more way. You don't need to map into 1 plus GSS. You map this S-plane contour into GSS and look at the encirclement of -1. That encirclement of -1 is again same. And you can write it equal to P minus Z, where P and Z are the poles and zeros of 1 plus GSHS. Okay, if you are mapping this S-plane contour into GSHS, and if you are looking the encirclement of -1, if you are looking the encirclement of -1, what does it mean? It means that encirclement will be P minus Z, where P and Z are poles and zeros of 1 plus GSHS inside this S-plane contour. Okay, it has to be clear in your mind. Okay, so let me tell you once again. If you have S-plane contour, now we have two situations. Think carefully, okay? Think carefully. If you have S-plane contour, let's say it's like this. The S-plane contour is like this. So we have taken entire right half. We have taken entire right half, okay? This is my entire right half. S-plane contour is this. This is j omega x's, okay? And this is r e to the power j theta. R tends to infinity, okay? So we have taken entire right half S-plane. This is S-plane contour. Now what I'm doing is I'm mapping this S-plane contour into GSHS. I'm mapping this S-plane contour into GSHS plane. And let's say the resultant contour is like this. Let's say this is the resultant contour. And the arrow is like this, okay? This is the resultant contour, guys. This is the resultant contour into GSHS plane. Now, if you are looking the encirclement of origin, let me write it like N0. If you are looking the encirclement of origin, then that will be equal to P minus Z or Z minus P. But these zeros and poles are the poles and zeros of GSHS inside this S-plane contour. This P and Z are the poles and zeros of the GSHS inside this S-plane contour. But if you are looking the encirclement of -1, if you are looking the encirclement of -1, then it will be again P minus Z or Z minus P. You have to take it positive. Either you write it like P minus Z or Z minus P. If you are looking the encirclement of -1. Now this P and this Z are the poles and zeros of 1 plus GSHS. They are not poles and zeros of GSHS. They are the poles and zeros of 1 plus GSHS. Okay. So it has to be very clear. If you are mapping this S-plane contour into GSHS, and if you are looking the encirclement of origin, or if you are looking at the encirclement of -1. If you are looking at the encirclement of -1, what does it mean? It means the encirclement of -1 has to be P minus Z, and the P and Z are the poles and zeros of 1 plus GSHS inside S-plane contour. If you are looking the encirclement of origin, that encirclement will be N naught. It is equal to P minus Z or Z minus P. Here P and Z are the poles and zeros of GSHS inside this contour. It has to be very clear. We are interested in the zeros of 1 plus GSHS. We are interested in Z, zeros of 1 plus GSHS. To find that, we need to find the poles of 1 plus GSHS inside this S-plane contour. How to find that? How to find the poles of 1 plus GSHS inside this S-plane contour? How to find that? We know that the poles of 1 plus GSHS and the poles of GSHS are same. So if GSHS is provided to you, we can find easily the poles of GSHS inside this S-plane contour. We can easily find. The same pole will be for 1 plus GSHS. You can put here and you can calculate the value of Z. You can calculate the value of Z. And you can comment on the closed loop system stability. I hope it is clear, everyone. Okay. Sir, any Nyquist system consists of a hysteric traveling salesperson would be sufficient algorithm to check stability. Okay, that's such a nice person you are. Okay. Sir, control के लिए signal की requirement है क्या? मैं सीधा आपसे control पढ़ रहा हूँ. हाँ, थोड़ा बहुत. Because to understand the basic system, you have to go for the Laplace transform. Laplace transform की आपको जरूरत पड़ेगी, ठीक है? Okay, guys. So I told you about this concept. Now let's apply this. Let's say I have GSHS. GSHS is given as maybe 2 divided by S into S plus 1, or maybe let's take 12 divided by S plus 1, S plus 2. Okay. And the S-plane contour is given to you. The S-plane contour is given to you. Okay. Let me show you the S-plane contour. One pole is lying here, one pole is here, and one pole is here. So I told you that while taking the S-plane contour, you have to include or exclude this pole location. So what I'm doing is I am taking like this. I'm including this. Okay. And I'm taking the orientation as clockwise, or you can take anti-clockwise. It's up to you. Okay. But I'm including this pole location. I'm including this pole. Now, if you map this S-plane, entire S-plane into GSHS, the resultant mapping will look like this. You have done this in the previous class. So the resultant mapping will look like this. It will go like this, okay? And then it will go like this, okay? And then it will go like this, okay? So this was the mapping. If you are mapping this entire S-plane contour, it will be like this. This point will be -2. You can check it. Using polar plot, if you know how to draw the polar plot, you can check that this point is -2. Okay. Now this is my GSHS. If you are looking the encirclement of origin in GSHS plane, if you are looking the encirclement of origin, remember what you are doing. If you are looking the encirclement of origin, let's say, then you are writing P minus Z or Z minus P. If you are looking the encirclement of origin, that has to be P minus Z or Z minus P. Now you know that one pole is lying inside this contour. One pole is lying inside this contour and there is no zero inside this contour. There is no zero inside this contour. So one pole is lying inside this contour and there is no zero inside this contour. So the number of encirclement of origin has to be 1. The number of encirclement of origin has to, it's not visible here, but you can directly see that one pole is inside this contour and there is no zero inside this contour of GSHS. So if you are looking the encirclement of origin, then that encirclement of origin will be P minus Z or Z minus P, and this P and Z are the zeros and the poles of the GSHS inside this contour. Okay. So you can directly see that the number of encirclement has to be, using this formula, you will get 1. And that encirclement will be opposite to this direction. Okay. Opposite to this. It means this is clockwise. So that encirclement of origin will be anti-clockwise and one time origin will be encircled. Now, if you are looking the encirclement of -1, if you are looking the encirclement of -1, then what you need to do? the encirclement of -1 is equal to either P minus Z or Z minus P. Now here the poles and the zeros are the poles and zeros of 1 plus GSHS inside this S-plane contour. Here the P and Z are poles and zeros of 1 plus GSHS inside S-plane contour. Inside S-plane contour. You have to be very clear. Okay. Here the P and Z are the poles and zeros of 1 plus GSHS inside this S-plane. Now how, what is the number of encirclement of -1? Tell me. The number of encirclement of -1 is only 1. You can see that. Only one time it is crossed. You can draw line like this, or you can draw the line like this. If you are drawing the line like this, then also you are getting the one encirclement. How? It is crossing like this, it is crossing like this, and it is crossing like this. It means this line is going away from the line, this line is going, so they will cancel, no? They will cancel, only one encirclement is there. So the number of encirclement of -1 is 1 only. Number of encirclement of -1 is 1 only, and that will be equal to, tell me guys, either P minus Z or Z minus P. Now we need to calculate this Z to check the closed loop system stability, because we know that the zeros of 1 plus GSS, these are the poles and zeros of 1 plus GSS inside S-plane contour, and we are interested in the zeros of 1 plus GSS because the zeros of 1 plus GSS are actually the poles of closed loop system. They will tell us about the closed loop system stability. That's why we are more interested in the zeros. Okay, now how to calculate these zeros? We need to find the poles. The poles of GSHS, the poles of 1 plus GSHS inside this S-plane contour. We need to find that. Now, how to calculate that? We know that the poles of 1 plus GSHS and the poles of GSHS are same. We know that. I told you the basic thing. I told you the basic thing here. The poles of GSHS and the poles of 1 plus GSHS are the same. It means the poles of GSHS are these poles, and the poles of 1 plus GSHS are also the same. How many poles of 1 plus GSS are inside this contour? One pole. One pole is inside this S-plane contour. So what you can do is, the poles of 1 plus GSS inside this S-plane contour is 1. So you can put 1 here. Okay. So if I put 1 here, then you'll get Z equal to 0. Okay. So P has to be 1. So Z came out to be 0. It means there is no zeros of 1 plus GSS inside this S-plane contour. And we know that the zeros of 1 plus GSS are actually the poles of closed loop system. So there is no pole of closed loop system inside this S-plane contour. The closed loop system is stable. Closed loop system is stable. Okay, I hope it is clear, everyone. The closed loop system is stable. This way you can check. So you have to be very careful. You are mapping into GSS plane. You are mapping into GSS plane. If you are looking the encirclement of origin, which pole and zeros are required here? And if you are looking at the encirclement of -1, which poles and zeros are required here? Okay, so it has to be very clear, guys. Otherwise, you will make mistake. Okay, so this is the very interesting case. This is the most interesting part, and this is the most important part that you need to be very clear. Okay, I hope it is clear. I hope it is clear. In GSHS, if you are looking at origin or looking at -1, that will decide. This P and Z meaning of P and Z are different in different cases. Okay. Now, let me give you one interesting case. Let me tell you one interesting case. And that interesting case is, let's say you have S-plane contour. Let's say you have S-plane contour. So I have only 5 minutes. So let's say you have S-plane contour. Now I want reply from you all, and you can reply in the chat section. Okay, let's say this is my S-plane contour, and what you are doing is, wait, this is my S-plane contour. Okay, this is my S-plane contour, and what I'm doing is, I'm mapping this S-plane contour into 1 plus GSS. I am mapping this S-plane contour into 1 plus GSS plane. Guys, be careful. Be careful. I am mapping this S-plane contour into 1 plus GSS plane, and it is like this. Okay, it is like this. And here it is origin, here it is 1. Here it is 1. This is origin, and this is 1. Okay. Given that closed loop system wait a minute. Given that the closed loop system is stable, given that the closed loop system is stable, it is given that the closed loop system is stable, find the number of zeros of GSHS. Okay, this is 0, this is 1, this is 2, and this is 2.5. Okay, these are the points, guys. Actually, I should not tell you this point because this is not required. This is 2, this is 2.5. Okay, okay. So find the number of zeros of GSHS inside S-plane contour. Inside S-plane contour. Tell me, guys. You have to find it. This is a very classical question. Okay, this is a very classical question. Let me show you. Let me repeat this question. This is S-plane contour, and this S-plane contour is given clockwise. Okay, this S-plane contour is given clockwise, and this S-plane contour is mapped into 1 plus GSHS. Okay, and after mapping, this is the final 1 plus GSHS plane contour. This is the final 1 plus GSHS plane contour. It is given that the closed loop system is stable. It is given that the closed loop system is stable. Okay, guys. It is given that the closed loop system is stable. Fine. We need to find the number of zeros of GSHS inside this S-plane contour. Number of zeros of GSHS. Remember, GSHS. Okay. So you have to comment on this. You have to tell me the answer in the chat section. Okay. You have to tell me the answer in the chat section. This is very important question, and I hope you will love this question. If you have understood all the concept, you will love it. Okay. So please think about it and tell me the answer in the comment section. So time is over because it's already 40 minutes. So I have taken the class for 40 minutes. So now the time is over, and in the next class, what I'm going to do is, I'm going to again go deeper into that. Okay. Let's go deeper into that, and let's try to apply and understand this concept more and more. Okay. And then at the last, I will tell you the trick also. In the next class, I will also tell you the trick, how to apply direct trick to check the Nyquist stability. Because you have seen in the previous class that you have to map this entire thing. First you have to map j omega, and then you have to map this, and then you have to map this, and then, so it's a lengthy process. So without mapping, how can you get the answer using the Nyquist contour? Okay, so that I will tell you in the next class. Okay, so I think it's time to stop here, and please reply this question. Please tell me the answer. What is the answer? Think about it. It's a very good question, and let's stop the class here. Okay, so guys, that's all for today's session, everyone. I hope you enjoyed. Don't forget to subscribe our channel and like this session and press the bell icon. Okay, we have our mobile app on the Google Play Store. Go to the Google Play Store, download it, and there also you can find some free lectures. Okay, so that's all for today's session. Thank you and take care. Bye.